On November 17th, NASA continues to delay the release of high-resolution images from the HiRISE camera on the Mars Reconnaissance Orbiter. Behind this delayed decision, there is clearly something difficult to explain. The data on ThreeI Atlast captured by HiRISE when Atlas skimmed near Mars's orbit have been held back for more than 40 days, long enough for the community to start questioning the level of scientific transparency. Before that, Atlast had already passed perihelion without breaking apart like a typical comet. On the contrary, it became more complex with at least 7 stable jets that seemed to suggest an active structure inside. Atlast has also stirred controversy with a tail reversed toward the Sun, a phenomenon that is hard to attribute solely to geometric effects, forcing scientists to consider 2 possibilities at the same time: either natural sublimation from a special vent on a rotating surface, or a form of active propulsion system cleverly disguised. The task of science is to distinguish between what is measured and what is inferred, allowing both scenarios, an extremely unusual natural comet and a technological object, to be modelled, tested, and ultimately confirmed or ruled out by data rather than by prejudice. Right now, let us continue to explore why NASA has remained silent for 40 days about the latest images of ThreeI Atlast. Is there some hidden mystery that we do not yet know about? High above the rust-red planet, the Mars Reconnaissance Orbiter circles in routine silence, its HiRISE imager turned outward toward Atlast. In that narrow window of days, ThreeI Atlast moves into the field of view as a faint speck against the black. For the first time, Atlast approaches a human probe closely enough that every pixel could matter. Engineers built HiRISE to read the fine grain of Martian sand dunes and boulder fields. Now the same instrument is asked to study ThreeI Atlast, a visitor born far from our Sun. Each exposure that HiRISE records could resolve the outline of Atlast's nucleus and the geometry of its jets. In this quiet geometry, Mars becomes the bystander, and Atlast stands alone on a stage of vacuum and light. Observers on Earth know the encounter is coming and track ThreeI Atlast in ephemeris tables and planning notes. Atlast will pass tens of millions of kilometers from Mars, close by cosmic standards, yet beyond any ground-based instrument. To the people watching trajectories, ThreeI Atlast is no longer just an odd curve in a simulation. The idea that HiRISE may already have captured that face turns Atlast from a distant calculation into an intimate question. No press release accompanies these days of careful imaging, only quiet entries in command logs and downlink schedules that mention Atlast by code and timestamp. In that quiet ThreeI Atlast slides past the orbit of Mars and continues sunward, carrying questions no one can yet put into words. Somewhere in the spacecraft's memory, chips frames of Atlast sit as raw numbers waiting to be decoded, calibrated, and finally seen. By the time the data begins its slow journey back toward Earth, Atlast has already left Mars behind, and the real story is about to begin. When the commands to image ThreeI Atlast are finished, and the spacecraft has done its work, the silence begins. HiRISE has stared into the darkness, recorded the faint outline of Atlast near Mars, and stored those frames deep in solid-state memory. From there, ThreeI Atlast should follow a familiar path or bits through the deep space network calibration on the ground, then a quiet public release. For a while that script seems plausible. A government shutdown is cited as the first reason for delay, and ThreeI Atlast becomes another line in a long backlog of data. Engineers and scientists can point to frozen budgets and paused processing pipelines as simple earthly explanations for why Atlast has not yet appeared. Days pass, then weeks. The shutdown ends, offices reopen, backlogs begin to clear, and other Mars data slowly flows out again. ThreeI Atlast, however, remains conspicuously absent from any archive browser. A curious researcher or amateur might check. The brightest, sharpest images of Atlast taken near Mars stay on the far side of a password prompt and an internal review queue. By mid-November, more than 40 days have passed since HiRISE first caught ThreeI Atlast near the orbit of Mars. In that span, Atlast has already swept through perihelion, changed its appearance, and moved on along its hyperbolic escape. For a time-sensitive target, the delay is not just an inconvenience. The delay shapes what the community can still learn from Atlast. Astronomers trying to model jets, dust, and non-gravitational forces rely on guesses, because the best resolved geometry of ThreeI Atlast is still unseen. The planning of follow-up observations, the tuning of telescopes, and the chance to test rival hypotheses about Atlast are all dulled at the edges. From the outside, no one can tell whether the hold on Atlast is a mundane bureaucratic lag or a sign of intense internal debate. Either way, the choice to keep ThreeI Atlast off the public record for this long becomes part of the story that future data will have to explain. For astronomers trying to work in real time every day, that ThreeI Atlast stays hidden behind unpublished frames stretches the distance between theory and reality. At the moment when Atlast is changing fastest, the sharpest view of its nucleus and jets exists only as an internal asset, not a shared foundation for the whole community. In the simplest version of the story, the delay around ThreeI Atlast is just an administrative shadow, trailing behind a government shutdown. Processing queues are long, staffing is thin, and Atlast happens to fall on the wrong side of a bottleneck. If that is all, the consequence is still serious but familiar by the time the community finally sees Atlast in detail. The best window for coordinated observations has already closed. Yet the longer the silence lasts, the easier it becomes to imagine another scenario. Maybe inside mission teams, ThreeI Atlast has triggered disagreement about how to interpret the images, about what to call certain features, about how bold any public statement should be. If the geometry of Atlast's jets or the outline of its core looks too strange, the instinct might be to pause to argue to recheck every calibration twice. From the outside, that instinct is hard to distinguish from something more troubling. Researchers who build models of non-gravitational acceleration and dust dynamics now have to decide whether to wait for ThreeI Atlast or to publish without the most decisive constraints. Follow-up proposals that might have targeted Atlast with other instruments lose their urgency as the object moves away, leaving only what could have been. In that light, ThreeI Atlast becomes more than a physical anomaly. Atlast becomes a quiet test of how open our science really is when the data refuse to fit. If a single set of images can shift the balance between a natural and a technological explanation, how long is it acceptable for those images to remain unseen? At the edge of sleep, the question lingers when the next ThreeI Atlast appears. Will we trust the sky enough and trust each other enough to let everyone look at it in time? Long before telescopes learned the name, ThreeI Atlast astronomers were tracing quiet curves on sky charts. They were looking for orbits that did not close tracks that never bent back toward the sun. The first time they saw such a path, they called it ʻOumuamua, and the second they named ThreeI Borisov. Each time the orbit was hyperbolic, an open line that said this visitor is not from here. When ThreeI Atlast was finally recognized, the shape of its path told the same story. The trajectory of Atlast is not a gentle ellipse like a planet, nor the stretched oval of a long-period comet. ThreeI Atlast follows a hyperbolic track with just enough excess speed that the sun cannot hold it. Once Atlast swings through the inner system, gravity will curve the path but never close it into a loop. On paper, the numbers are simple. The eccentricity of ThreeI Atlast's orbit is greater than 1 the signature of an interstellar origin. The inbound velocity of Atlast measured far from the sun matches a background of stars that share no special tie to our own. ThreeI Atlast is not falling back home. Atlast is passing through. Yet even in that clean mathematics, a quiet strangeness hides. The galaxy is wide and the volume of space is enormous, but we have already seen 3 such travellers in a short span of years. Each interstellar object, including ThreeI Atlast, arrives from a different direction with a different speed, writing its own one-time line across the sky. For some researchers, the appearance of Atlast so soon after ʻOumuamua and Borisov feels less like a rare accident and more like the beginning of a pattern. Lying in the dark, you can imagine the solar system as a small room in a vast building. ThreeI Atlast does not belong to the furniture of that room. Atlast is a passerby glimpsed in the doorway. In the next chapter, the focus will shift from the path of Atlast to the shape of its tail, and to the way that tail seems to lean oddly back toward the sun. Before ThreeI Atlast ever brushed past the sun, the first clear portraits came from far above Earth. In July 2025, the Hubble Space Telescope turned its gaze toward Atlast and recorded a view that quietly unsettled textbook expectations. On those images, ThreeI Atlast did not just show a single tail streaming away from the sun as most comets do. Instead, Atlast displayed a strange secondary structure, a narrow streak of material that seemed to reach back toward the sun itself. For generations, students have been taught a simple rule. Solar radiation pressure and the solar wind push dust and ionized gas away from the sun so comet tails point outward. ThreeI Atlast on the Hubble frames appeared to disobey that rule in a subtle but persistent way. In the faint geometry of those pixels, Atlast carried what observers call an anti-tail, a feature that seems to lean sunward rather than outward. There is a known natural explanation for some anti-tails. Under special viewing angles, perspective can make a sheet of dust in the comet's orbital plane appear as a spike pointing toward the Sun. Applied to ThreeI Atlast, that first hypothesis would say that Atlast is ordinary, and only the angle is strange. The apparent sunward extension would then be a trick of alignment, not a true challenge to the forces that act on comet dust. But the details of the Hubble geometry complicate that comforting picture. The telescope saw ThreeI Atlast from a vantage only about 10 degrees off the Sun's direction, a nearly edge-on view of the dust plane. At that angle, the structure associated with Atlast behaves less like a flat sheet, and more like a physical spike resisting the outward push of light. The anti-tail of ThreeI Atlast begins to look less like an illusion, and more like a real stream of material pushing back against radiation pressure. Lying in the dark, you can imagine the Sun shining steadily, while one thin filament tied to ThreeI Atlast leans against the flow. That quiet defiance becomes the first small question that Atlas whispers into our models. In the next section, the story will move from the shape of that sunward streak to the deeper question of what kind of engine could sustain such a pattern around Atlast. If the anti-tail of ThreeI Atlast were only a trick of perspective, the story could rest there. But the viewing geometry refuses to cooperate with that easy answer. When Hubble watched ThreeI Atlast in July, the telescope saw Atlast from a vantage only about 10 degrees off the Sun's direction. In that almost edge-on view, the dust plane tied to Atlas should have flattened into a thin sheet, not sharpened into a clean sunward spike. This is where the discussion around ThreeI Atlast quietly shifts from simple optics to the mechanics of how material leaves a body. One natural line of thought imagines a specific vent on the rotating surface of Atlast, a patch where sunlight penetrates deeply into volatile rich layers. As that area rotates into daylight 3, Atlas could release gas and dust in a focused plume, giving the particles enough initial momentum to appear to push back toward the Sun for a time. In this picture, the anti-tail of Atlast is not fighting solar radiation so much as emerging from a clever, if accidental, combination of spin vent location and timing. Yet even this refined model leaves questions on the table. How finely tuned would the orientation of ThreeI Atlast and the placement of its vents have to be to sustain a coherent sunward feature? For how long could Atlast keep that alignment before rotation and outgassing changed the pattern beyond recognition? The more constrained the natural explanation becomes, the more ThreeI Atlast starts to feel like a system balanced on a narrow ledge of possibilities. That narrowness opens the door to a more speculative thought. What if the material leaving ThreeI Atlast is not just venting, but thrust? In such a scenario, Atlast would be using directed jets of gas and dust as a form of propulsion deliberately angled to adjust its path while hiding within the behaviour of a comet. To an observer far away, ThreeI Atlast would still look like a dusty body, responding to sunlight even as subtle changes in its orbit carried the imprint of guidance. Drifting towards sleep, you do not have to choose between these pictures of ThreeI Atlast. You only have to notice how a small sunward streak in the darkness can stretch our sense of what is possible. In the next chapter, attention will move with Atlast toward perihelion to see how this visitor behaves when the full heat of the Sun turns every vent and every suspected engine to its highest setting. By late October 2025, every ephemeris led to the same moment, a narrow point on ThreeI Atlast's path, where the visitor would pass closest to the Sun. On 29th October, ThreeI Atlast reached perihelion, entering a zone where solar light and heat press far more harshly on fragile structures. For a typical comet, perihelion is a trial by fire, a place where buried ice turns to gas violently, and dusty shells can crack or fly apart. Observers watching Atlast expected that this would be the point where the visitor might finally show whether it was robust or fragile. In the days leading up to that passage, models of ThreeI Atlast painted a cautious picture. Many predicted that Atlast could shed large amounts of material brightening and then fading as chunks of the nucleus broke away. Others imagined a quieter outcome where ThreeI Atlast would simply grow a broader, messier coma and tail as new vents opened under the rising heat. Behind every line of code and plotted curve was the same assumption: perihelion would strip Atlast down, not build Atlast up. The physics behind those expectations is straightforward. As ThreeI Atlast swings close to the Sun, sunlight digs deeper into the surface, reaching volatile pockets that stayed dormant farther out. Gas rushes out of those layers, dragging dust and sometimes rock, putting mechanical stress on whatever solid structure holds Atlast together. Given enough stress, ThreeI Atlas could have shattered, joining the long list of comets that do not survive their closest approach. But when the worst of the heating passed and new observations arrived, ThreeI Atlast had not dissolved into an expanding cloud. Atlast emerged from perihelion, still present, still coherent, and soon appeared to wear a more elaborate pattern of jets and structures than before. Instead of simplifying the visitor, the Sun seemed to have encouraged ThreeI Atlast to reveal new layers of behaviour. In the next section, the focus will move to that post-perihelion appearance, and to how Atlas seems to grow more organised exactly where many objects fall apart. When the first post-perihelion images trickled in, astronomers leaned closer, expecting to see a wounded ThreeI Atlast. They looked for ragged edges for a swollen chaotic coma that would signal a nucleus crumbling under stress. Instead, ThreeI Atlast appeared with lines and structures that seemed more defined than before its brush with the Sun. Under higher solar input, many comets behave like melting sculptures, losing detail as ice gives way and dust clouds thicken. ThreeI Atlast did not follow that script. The envelope around Atlas showed hints of layered structure, subtle gradients and emerging jets that gave the whole scene a sense of internal organisation. From one night to the next, observers tracking ThreeI Atlast began to notice repeating shapes in the coma. Certain features around Atlast brightened and faded in patterns that did not look like pure randomness. The impression grew that ThreeI Atlast was not merely surviving perihelion, but using that intense phase to unlock a more complex mode of activity. In quiet observatories, late-night teams overlaid images and measured angles trying to decide what ThreeI Atlast was telling them. The more carefully they compared those frames, the more Atlas seemed to exhibit coherence rather than collapse. Jets emerging from ThreeI Atlast lined up along preferred directions, as if tied to enduring structures deep within the nucleus. For some, this was still within the bounds of a highly stressed, naturally fractured body. A network of cracks and vents inside ThreeI Atlast could in principle channel gas in ways that mimic design. For others, the specificity of those directions made Atlast feel less like a random ruin, and more like a system responding in an ordered way to a predictable surge of energy. Lying in the dark, you can picture ThreeI Atlast leaving perihelion not as debris, but as a reshaped traveller with new patterns unfolding around it. The next part of the story will narrow in on those patterns, asking how many jets surround Atlast, and whether their choreography belongs entirely to chance. As more observatories joined, watching the new face of ThreeI Atlast began to come into sharper focus. By early November, stacked and processed frames from patient ground-based telescopes showed that Atlast was no longer marked by a single dominant tail. Instead, ThreeI Atlast seemed wrapped in a fan of distinct jets, narrow streams of material fanning away from the nucleus. On composite images released around November 9th, careful inspection revealed at least 7 separate jets tied to ThreeI Atlast. Some of those jets from Atlas stretched roughly along the expected line, away from the Sun shaped by radiation pressure and the solar wind. Other jets around ThreeI Atlast leaned at striking angles, carving their own directions through the coma in ways that were harder to file under routine behaviour. Mapping those features, astronomers traced each jet of ThreeI Atlast back toward a compact central region, the hidden nucleus that no telescope could quite resolve. From the outside, ThreeI Atlast looked like a small lantern sending out beams into space, each beam marking a favoured route for gas and dust to escape. Night after night, the same jets reappeared around Atlast, shifting subtly in brightness, but holding their orientations as if anchored. The pattern invited a natural explanation first. Inside, ThreeI Atlast arrays of fractures and cavities could channel sublimating ice into discrete vents, each vent feeding one of the observed jets. As ThreeI Atlast spins, different vents would turn sunward in sequence, creating a choreographed flicker without any need for intention. Yet the regularity of the pattern also suggested a more demanding geometry. To keep 7 or more jets of ThreeI Atlast stable over many days, the internal structure would have to resist the very stresses that perihelion should have amplified. The more precise the alignment, the more ThreeI Atlast started to resemble a device with preferred exhaust ports, rather than a random pile of ice and dust. Lying in bed, you can imagine ThreeI Atlast slowly turning a cluster of invisible nozzles, breathing in cycles as sunlight sweeps across the surface. Whether those jets are accidental vents, or something more like engines, they carry ThreeI Atlast into the next layer of mystery. The following section will turn from their number and shape to the deeper question of what those jets imply about how Atlast is being pushed, and who or what is doing the pushing. Faced with the post-perihelion behaviour of ThreeI Atlast astronomers, are pulled between two competing ways of telling the story. One narrative treats ThreeI Atlast as a wildly stressed but natural comet, shaped by fractures, buried ice, and ordinary sunlight. In that first model, perihelion acts like a stress test that opens new vents across the body of ThreeI Atlast. Gas and dust escape from those vents, and the spin of Atlast organises outflow into discrete jets that just happen to trace stable directions. The apparent symmetry around ThreeI Atlast then becomes an emergent pattern, carved by internal faults, rotation rate, and the angle of solar heating. This picture keeps ThreeI Atlast firmly inside known physics, asking only that nature be allowed a taste for intricate, fragile arrangements. The second model begins with the same observations, but gives ThreeI Atlast a different role. Instead of a random network of cracks, the internal structure of Atlast is imagined as a set of deliberate channels, exhaust ports that act like engines. In that speculative frame, perihelion for ThreeI Atlast is not just a stress test, but an activation phase when carefully placed thrusters wake up. Gas flow then becomes guidance, and the fan of jets around ThreeI Atlast doubles as a hidden propulsion system masked by a comet-like coma. Neither model can claim victory with the data in hand, and ThreeI Atlast sits in the uncomfortable space between them. The natural scenario asks us to accept that a small, fragile object like Atlast can maintain multiple stable jets through the harshest heating of its life. The engineered scenario asks us to consider that ThreeI Atlast might be a device built to ride starlight and gravity, while pretending to be debris. Both stories fit some of what is seen, and both leave parts of ThreeI Atlast unexplained. Lying in the dark, you are not required to choose. You only have to notice how ThreeI Atlast forces the line between nature and design to blur, inviting the next chapter to look more closely at how Atlast is actually being pushed through space. To move beyond pictures and shadows, the story of ThreeI Atlast has to become a story of numbers. Beautiful images of jets and tails around Atlast can hint at structure, but they cannot by themselves decide between a fractured comet and a guided machine. To test those two models, astronomers need to know exactly how fast material leaves ThreeI Atlast and exactly how Atlast responds in its orbit. In practice, that means two kinds of measurements. The first is velocity in the jets of ThreeI Atlast, the speed of gas and dust streaming away from the surface. By reading the tiny Doppler shifts in spectral lines, observers can estimate how rapidly material tied to Atlast is moving toward or away from us. If the flows from ThreeI Atlast are only a few hundred meters per second, they sit comfortably in the range expected from ordinary sublimation. If some components rush out at several kilometers per second, they begin to look more like exhaust from an engine than gentle venting. The second kind of measurement watches how ThreeI Atlast moves as a whole. Precise astrometry tracks the position of Atlast night after night, comparing its path to the curve predicted by gravity alone. Any consistent deviation shows up as non-gravitational acceleration, a small but telling nudge that ThreeI Atlast experiences as its jets push back against space. For a purely natural comet, that push should correlate in familiar ways with brightness changes and outgassing rates. For a controlled object, ThreeI Atlast might exhibit shifts that appear timed or directed less like weather and more like steering. Lying with your eyes closed, you can imagine the problem as two simple questions written beside the name ThreeI Atlast. How fast does material leave Atlast, and how exactly does Atlast respond? Until those numbers are known, the two stories about ThreeI Atlast remain balanced, and the next sections will turn to the first real clues that hint at extra forces in play. In the first model, ThreeI Atlast is treated as a comet pushed only by sunlight and heat. When the sun warms the surface of Atlast, buried ice turns to gas and escapes into space. That escaping gas from ThreeI Atlast drags dust grains with it, forming jets and tails without any need for intention. In this natural picture, the velocities in the jets of ThreeI Atlast stay modest. Spectra taken from Atlast would show line shifts corresponding to a few hundred meters per second, not more. Such speeds fit comfortably inside the well-known range for sublimation-driven outflows from other comets, anchoring Atlast in familiar physics. As the activity rises and falls, ThreeI Atlast brightens and dims in step. When more surface area on Atlast turns sunward, more gas escapes and the coma grows thicker. At those times, the small non-gravitational accelerations seen in the orbit of ThreeI Atlast would naturally increase. In that case, the orbit of ThreeI Atlast does not need hidden engines to curve it. The path of Atlast would be explained by the rocket effect, the gentle cumulative push of many tiny jets acting over weeks. The more Atlast sheds mass in one direction, the more its trajectory shifts in the opposite direction, just as with other active comets. Under this model, the structure in the jets of ThreeI Atlast comes from geology rather than design. Cracks-layered deposits and cavities inside Atlast funnel gas into preferred routes shaping discrete plumes. The apparent symmetry around ThreeI Atlast then becomes an emergent pattern of stress lines, and spin state, not a blueprint. Drifting towards sleep, you can think of ThreeI Atlast as a fragile, icy stone being sculpted from the outside. In this telling, Atlast is remarkable mainly because we are watching so closely, not because nature has broken its own rules. The next section will keep the same data in view, but ask what they look like if ThreeI Atlast is not only venting but steering. In the second model, ThreeI Atlast is not just venting, Atlast is manoeuvring. Here the jets around ThreeI Atlast behave less like accidental cracks and more like arranged exhaust ports. Instead of random fractures, the interior of Atlast resembles a network of channels designed to route gas in specific directions. Under this view, perihelion becomes the moment when ThreeI Atlast brings a hidden propulsion system fully online. In such a scenario, the velocities in the jets of ThreeI Atlast need not stay modest. Spectra from Atlast could show components moving at several kilometers per second speeds more typical of engineered exhaust than gentle sublimation. Those faster flows from ThreeI Atlast would carry more momentum, giving each jet the power to nudge the orbit in a chosen way. To a distant observer, the same plumes would still look like natural comet activity, letting Atlast hide its guidance behind familiar physics. In the orbital record, ThreeI Atlast would leave subtle fingerprints of this behaviour. Instead of non-gravitational acceleration that simply rises and falls with overall brightness, the shifts in Atlast's path might appear timed or directional. ThreeI Atlast could show small course changes clustered around specific phases of rotation or points along its trajectory. To someone mapping those changes, the pattern would feel less like weather and more like a sequence of gentle steering burns. This model asks more of ThreeI Atlast, but it also answers some puzzles more cleanly. The stability of multiple jets, the survival of ThreeI Atlast through perihelion, and the organised geometry of its outflow all become features of a designed system. In that light, Atlast becomes a probe riding gravity and sunlight, while quietly trimming its path with buried thrusters. As you drift towards sleep, you do not have to decide whether ThreeI Atlast is a comet or a craft. You only have to imagine that somewhere in the darkness, Atlast might be using streams of vapour, not just to shine, but to choose where it goes next. Among all the missing pieces in the story of ThreeI Atlast, the unpublished HiRISE frames may be the most decisive. Those images of ThreeI Atlast were taken when Atlast slid close to Mars at a distance where the camera could resolve features far finer than any ground-based telescope. In that brief encounter, HiRISE turned ThreeI Atlast from a speck into a structured object, something whose coma and jets could be traced in sharp detail. With proper processing, each frame of ThreeI Atlast could reveal where individual jets emerge from the envelope and how those jets curve as they leave the nucleus. By stacking and modelling those views, astronomers could reconstruct the three-dimensional geometry around Atlast, the tilt of the spin axis, the distribution of active regions, the thickness of the surrounding coma. In the natural model, that geometry around ThreeI Atlast should line up cleanly with expected stress patterns in a cracked, icy body. In the engineered model, the same geometry around Atlast might betray regular spacing alignment or symmetries that look more like hardware than geology. HiRISE also offers a kind of stillness that other instruments lack. Because the Mars orbiter watched ThreeI Atlast from a fixed vantage near the object, HiRISE saw Atlast without the same atmospheric distortions or rapidly changing viewing angles that complicate ground images. That stable view would let analysts follow how brightness and shape around ThreeI Atlast evolve over hours, tying the dance of jets directly to rotation. As long as those frames stay behind internal gates, the key test for ThreeI Atlast remains hypothetical. Researchers can only guess how strongly the data would favour one model over the other, and planning for future encounters with objects like Atlast has to proceed without that anchor. For some, the delay is just bureaucracy. For others, the silence around ThreeI Atlast feels like a pause held too long over a critical note. As you drift deeper into the night, the question lingers with the name ThreeI Atlast attached. When the sharpest view of Atlast finally appears, will the image confirm a stressed shard of ice, or suggest that a more deliberate structure has passed briefly through our reach? 5 days before perihelion, on 24th October 2025, a different kind of eye turned toward ThreeI Atlast. Far from city lights in South Africa, the Meerkat radio array swept the sky near the sun's glare, listening where cameras are nearly blind. On that night, Atlast was already diving inward too close to the sun for many optical telescopes to follow comfortably. While most instruments watched the brightness curve, Meerkat tuned its attention to the quiet, narrow fingerprints of radio lines. In the data that came back, astronomers found a set of discrete absorption features along the path of ThreeI Atlast. Those features lined up with the signature of hydroxyl, OH, a fragment that appears when ultraviolet light breaks apart water molecules. Instead of shining, Atlas showed up as tiny notches in the radio spectrum, places where background noise dipped because OH associated with Atlast had absorbed it. The detection told observers that water ice on or around ThreeI Atlast was being turned into gas and then into fragments in real time. For comet scientists, this part of the story sits comfortably inside known behaviour. Any active body like ThreeI Atlast warmed by the sun should release water vapour that later breaks into OH under solar radiation. Seen this way, Meerkat simply caught Atlas clearing its throat before the main performance at perihelion. The lines in the spectrum become a kind of quiet breath, a sign that Atlast is reacting to sunlight in a way that other comets have done before. Yet even within this natural frame, the timing and clarity of the signal from ThreeI Atlast stand out. Just days before its closest approach, Atlast announced that large reservoirs of volatile material were waking up ready to feed stronger activity. Lying in the dark, you can imagine those radio notches as the first faint sounds of Atlast, in a room where everything else is silent. In the next section, the focus will stay on these OH lines, asking how they fit the standard comet script, and how they set the stage for deeper questions about Atlast's true nature. On paper, the OH detection near ThreeI Atlast can be described in calm, familiar terms. When sunlight warms the surface of Atlas-buried water, ice turns to vapour, and that vapour later breaks under ultraviolet light into fragments like OH. Radio telescopes looking at ThreeI Atlast then see OH as small dips or peaks at very specific frequencies, the spectral fingerprints of those molecules. For ThreeI Atlast, Meerkat found features around 1.665 to 1.667 GHz, right where OH is expected to speak. Those numbers sit comfortably inside the standard catalogue that comet researchers use, so nothing about the raw identification forces ThreeI Atlast out of the ordinary. Given the timing just days before perihelion, ThreeI Atlast behaves like a textbook active comet beginning a phase of stronger outgassing. In that standard picture, there is no mystery at all. ThreeI Atlast releases water vapour, sunlight breaks that vapour into OH, and radio instruments record the result in the form of narrow lines. The strength and shape of those lines tied to Atlast then tell observers about the amount of gas and the pace of activity. What lingers in the background is where exactly those OH lines from ThreeI Atlast fall in the broader spectrum. The 1.665, 1.6667 GHz band sits near the upper edge of a region long nicknamed the waterhole, bracketed by the hydrogen line near 1.42 GHz, and the main OH transitions up to about 1.67. For decades, some SETI studies have treated that zone as a naturally quiet, symbolically rich place to search for interstellar communication, and ThreeI Atlast happens to light up right inside it. From a strict comet science perspective, this may be nothing more than coincidence, because those are exactly the frequencies where OH should appear, around any active body like Atlast. The physics that link ThreeI Atlast water and OH do not require any message or design. Still lying awake, you can feel a small unease around how comfortably Atlast speaks, in a band that humans once imagined as a meeting place for messages between stars. In the next section, attention will turn to that more speculative reading asking what the same data look like if ThreeI Atlast is not only venting water, but using a cloak of ice as part of a deliberate disguise. Among those who think about signals and disguises, the case of ThreeI Atlast feels less straightforward. The same OH lines that reassure comet specialists also catch the eye of researchers, who study how a technological object might try to blend in. To them, ThreeI Atlast does not only sit inside the waterhole by accident. Atlast becomes a demonstration of how a natural cloak might work. In that speculative frame, ThreeI Atlast is still covered in ice and dust, but the covering is part of the plan, not just leftover geology. A probe built across interstellar space could be wrapped in volatile material, so that when it nears a star, the outer shell behaves exactly like a comet. To anyone watching from afar, ThreeI Atlast would then look like any other icy body. Atlast would release water, generate OH, and light up the same radio lines. The advantage of such a disguise is subtle. ThreeI Atlast could pass through a planetary system under the same labels and assumptions used for native comets. If Atlast ever emitted intentional radio signals, They could ride on top of or hide within the natural noise created by OH in the waterhole band. Detection pipelines would treat those features as routine filing ThreeI Atlast away under activity rather than message. This idea does not claim that ThreeI Atlast is sending or receiving anything now. It simply asks whether a distant engineer imagining how to slip past another civilization's first filters might choose a design that makes Atlas look exactly like what telescopes already expect to see. 3i, Atlast in that story, becomes both actor and mask, probe and comet at once. Drifting towards sleep, you can let both pictures of 3i Atlast rest side by side. In one, Atlast is only reacting to sunlight. In the other, Atlast is using that same sunlight to power a carefully planned disguise. The next section will stay with the radio data and ask what more could be learned about these possibilities if the motions of gas around 3i Atlast were measured in finer detail. For now, the radio story of 3i Atlast is told mostly in outlines and hints. Meerkat has shown that OH is present around Atlast, but the full high-resolution spectra that would reveal how that gas is moving have not yet been placed in broad public view. Between the raw detections and the open archives, 3i Atlast sits in a kind of analytical pause. What observers most need from those spectra is not just the presence of OH, but its velocity field around 3i Atlast. Tiny shifts in the frequency of each line would show how fast the gas tied to Atlast is coming toward or moving away from us along the line of sight. By mapping those shifts at different positions, astronomers could draw a picture of how OH flows through the space around 3i Atlast. In the natural scenario, the OH around 3i Atlast would carry signatures of gentle sublimation. Velocities would cluster in the familiar range with smooth gradients tracing jets that fan out in directions set by sunlight and rotation. 3i Atlast in that reading becomes one more entry in a long list of active bodies whose gas motions look like weather, not machinery. In the more speculative scenario, the pattern around 3i Atlast could be sharper stranger. Some components near Atlast might show unusually high speeds or alignments that suggest collimated streams rather than diffuse plumes. The flow around 3i Atlast might organise into structures that resemble exhaust, with preferred directions that are hard to tie to simple surface cracking. Until those detailed spectra are shared and fully analysed, both stories remain suspended over the name 3i Atlast. Modelers can run simulations and guess what the data might say, but the definitive test of how gas leaves Atlast is still pending. As you lie in the dark, you can think of that missing velocity map as a quiet, unfinished drawing. A sketch that could tell us whether 3i Atlast is simply breathing in sunlight or shaping its own path with every molecule it lets go. By the time the main observing campaigns wind down, the story of 3i Atlast has split into two clear paths. In one, 3i Atlast is an extreme but still natural comet, a frozen remnant from another star sculpted by chance. In that natural model, every anomaly around 3i Atlast is folded back into the flexibility of comet physics. The sunward antitail of Atlast becomes a product of viewing geometry, and a vent placed just so on a rotating fractured nucleus. The multiple jets of 3i Atlast, including the ones that lean against intuition, arise from stress lines and layered ice deposits. The non-gravitational acceleration of Atlast is then nothing more than the integrated push of many small plumes over time. Even the OH lines near the waterhole become for 3i Atlast simply the expected whisper of water broken by sunlight. The second path treats 3i Atlast as a possible techno-signature, a device whose behaviour is partly masked by a cometary shell. In that speculative model, perihelion serves as an activation event for Atlast, lighting up carefully placed exhaust channels as the star's heat rises. The anti-tail and jet geometry of 3i Atlast become clues to deliberate thrust, with Atlast trimming its trajectory while staying within comet norms. The non-gravitational forces on 3i Atlast read like gentle steering corrections rather than unplanned rocket effects. The radio signature around Atlast sitting neatly in the waterhole is no longer just coincidence, but part of a tested disguise strategy. Neither story can yet claim to own 3i Atlast completely, and the current data can be arranged to favour either side. The natural scenario asks us to accept that 3i Atlast is an outlier in a universe already rich with extremes. The engineered scenario asks us to admit that 3i Atlast might be our first brush with designed hardware drifting between stars. As you lie in the dark, both images of 3i Atlast remain possible, and the next section will ask how science should move forward when the boundary between nature and technology grows this thin. For many people listening to the story of 3i Atlast, the second model, still sounds like something borrowed from science fiction. Engines buried in ice, a probe wrapped in a cometary shell at last trimming a path in secret. The easy reflex is to push that image of ThreeI Atlast into the same drawer as starships and movies. Science, however, cannot reject a possibility just because the story around ThreeI Atlast feels cinematic. What science owes to ThreeI Atlast is not belief, but a disciplined way of handling ideas. That discipline begins with a simple separation in the way we think about Atlast. Some statements about ThreeI Atlast are direct descriptions of measurements, positions, spectra, images, while others are stories we build to explain those measurements. When those two layers blur, the risk is not only that ThreeI Atlast will be misunderstood. There is a deeper risk that out of fear of sounding fanciful, researchers will refuse to even test certain explanations for Atlast. If no one is allowed to model a technological scenario for ThreeI Atlast, then one entire family of patterns is removed from the tools we can use. The data from Atlast may then be forced into shapes that feel safer, but fit less well. Hypothesis discipline means giving every serious, physically grounded idea about ThreeI Atlast a chance to stand next to the evidence. It means building models of extreme natural behavior for Atlast and parallel models that treat Atlast as designed hardware, then asking what each would predict. Most of those bold sketches for ThreeI Atlast will eventually be erased, but in the erasing we learn where the real boundaries lie. From the outside, this process can sound like storytelling, especially when ThreeI Atlast sits so close to the edge of what we know. The difference is that science does not stop with a dramatic twist for Atlast. It stops when predictions and measurements agree better than any rival account. Lying in the dark, you do not have to choose which picture of ThreeI Atlast you prefer. You only have to trust that somewhere quietly, every honest possibility for Atlast is being tested, so that when new data arrive, curiosity will be stronger than fear of being wrong.